Associate Professor Dr. Krishnapriya S. Vaani. Dr. Krishnapriya holds a PhD in microelectronics from NIT Calicut. Her research interests include microelectronics, microcoils for biomedical applications, and wireless power transfer. She will be speaking on the topic Recent Trends and Technology Change in IC Design and Manufacturing. Session എടുക്കുന്നതിനായി മാമിനെ സ്വാഗതം ചെയ്യുന്നു.
Thank you for the nice introduction. Good afternoon, everybody. കുറച്ച് പേരൊക്കെ UG students ഉണ്ടെന്ന് എനിക്ക് മനസ്സിലാക്കുന്നു. PG students are also there. So I would like to focus on the VLSI devices, especially in today's session. Not on all the VLSI trends, especially this focused on the semiconductor devices, okay, and what is going on in the device design area. The VAANI FDP ആയിട്ടുണ്ട് അറിയാമെങ്കിൽ സമീപകാല ട്രെൻഡുകൾ, അതായത് VLSI ഡിവൈസസിൽ വരുന്ന റീസെന്റ് ചേഞ്ചസ് ആണ് ഞാനിവിടെ സംസാരിക്കാൻ ഉദ്ദേശിക്കുന്നത്. നമുക്ക് ഹിസ്റ്ററി ഓഫ് സെമികണ്ടക്ടർ ഡിവൈസസ് അറിയാം അല്ലേ? It all started with the invention of vacuum tubes in 1905. Okay. Do you know who is the inventor of vacuum tubes? Can it be treated as a semiconductor device? Vacuum tubes, it's based on a thermally heated cathode and anode, basically two electrodes. Actually, there is no presence of any semiconductor material in that. But still it is treated as the first ever semiconductor device ever. Okay, and that was actually a major invention moving into the semiconductor or electronic circuit. Okay. And the computing equipment, ENIAC, that used around thousands of vacuum tubes, very bulky vacuum tubes that time. So that is where we thought of the significance of reducing the size of devices. Because the computer occupied an entire big room and all. Okay. And next comes the invention of the first ever semiconductor device, coin contact transistor. As you can see in the second column, it was invented by a set of three scientists. As mentioned here, John Bardeen, William Shockley, and Walter Brattain. And William Shockley, he was heading the team. And that was actually a contact transistor, where two contacts were made against a germanium-based material. Okay, and actually that device failed in its operation, though it could produce a bit of power lead. The current gain and all was poor. Okay, so that device would not succeed. The first ever transistor, which is treated as the first ever semiconductor device. Because the base material used was germanium. And next major invention, which is called as a junction transistor. As you can see, the other one was a simply coin contact transistor. And next comes the invention of junction transistor around 1950s, and that was developed by William Shockley. He can be treated as the father of electronics, William Shockley. And by then, it has been made as some primary components in the computing devices in those times, such as the one shown here in telephonic system and other radio, military equipments and all. Junction transistor, it was treated as a very primary invention coming to the junction devices. Okay. Then the major milestone, I should say, as the main powerhouse of the semiconductor era, which is that is integrated circuits, which we call as chips, right? So the IC chip, as you might know, it was invented by Jack Kilby, who was working at Texas Instruments, and I don't know whether that can be treated as an integrated device that time. In 1958, it was actually a combination of a few devices, such as a few transistors, resistors, capacitors, etc. It was combined together on a common substrate. But what's the true meaning of integration? Device integration? Can somebody tell me? Still, it is treated as the first ever integrated circuit, which was invented by Jack Kilby. He was working at Texas Instruments that time. Actually, that fueled the era of the true silicon age. Okay. So, in 1958, as we mentioned, it was only very few transistors, less than 5 in number, when it started off. Then, you know, where we are standing now, you can guess, it is around 15-16 billions of transistors in a tiny silicon chip, right? So, you know, the latest iPhone, Apple iPhone and all, it uses some A18 bionic chip. It consists around 16 billions of transistors. That is the transistors in its very latest form. Okay, so that is the growth of semiconductor device. The area of semiconductor device, it is growing at a very faster pace, and that growth is dictated by a very famous rule, a law. Most of you might know it. What is that? It is Moore's law, the law proposed by Gordon Moore. And sorry, I missed out the other major invention of MOSFETs. Okay, that is in 1960s. 1960s, the first MOSFET fabricated by a team at Bell Laboratories. And you might have heard of Robert Noyce. He is a co-founder of Intel Corporation. So he used one particular manufacturing process known as Honey's process to fabricate a circuit based on MOSFETs. That was realized on a single piece of silicon. So that also can be treated as some form of integrated form. Okay. Then, after 1960s, the circuits were developed out of RTL, resistor transistor level logic, RTL logic. And still then, as it was the beginning of integrated circuits, consisted of transistors which were less than 10 in number. Okay. Then, as I told you, the Moore's law started to dictate the growth of the IC chips. The number of transistors, you know, more components can be crammed into a single piece of wafer or substrate. Okay. So the number of transistors, you know, it doubles every 18 months. Okay, that is what is given by Moore's law. So can we say that the Moore's law it is being followed till date? Okay, we will see that. So in earlier days, the circuits were fabricated out of BJTs. BJTs were given much of the significance. But the problem compared to MOSFET, BJT has a higher amount of static power dissipation. So BJT could not be resorted for long for realizing integrated circuits. So later on, the significance of complementary MOSFET, that means utilizing P MOSFET and N MOSFET. I hope most of you know the basic components, N-type, P-type MOSFETs. Both were utilized together, which is called as a complementary MOSFET technology, CMOS technology. And I should say the first ever microprocessor, which was invented by Intel, which was marketed by Intel in 1971, that utilized only NMOS, N-type MOSFETs alone. Okay, and the purpose that time was to build an electronic calculator using that microprocessor chip in 1971. So, realizing the importance of CMOS, later on the microprocessors were built on CMOS technology, though the first one was realized using NMOSFETs. So, the advantages of CMOS technology, most of you may know. Primarily the power dissipation, the static power dissipation is very low. of course dynamic power is there, then the speed and the fabrication methods available, the standard process available for CMOS fabrication. Okay, all those favored the growth of CMOS technology from around 1975 onwards. And another major advantage given by the MOSFETs were the packing density could be improved. The number of chips that can be integrated within a single substrate. The packing density could be improved with the invention of this CMOS technology. Okay. So that is called as technology scaling dictated by Moore's law. You know the nodes, feature size is getting smaller and smaller. Okay, feature size actually refers to the smallest dimension available in an IC chip. It can be the width or length of the transistor, or maybe the distance between metal lines. Okay, anything. The smallest size is referred to as feature size in an IC. Okay, in an IC design. So, while you design an IC, these many factors need to be considered: the quantum effects, material and processing limits, okay, and power. You know the power, speed or bandwidth, then the timing parameters. They form a major triangle of circuit design. Okay, power, bandwidth, then the speed. The timing constraints. Okay. So all this decides the reliability of the IC chip as well. So here some transmission electron microscope images are shown for some of the feature sizes. 10 nanometer is shown, 13, 18 nanometers are shown here. So the gate length, as obviously gate length is less than 20 nanometer in these figures. So I would like to use that word feature size. Based on feature size, how the technology has been scaling, that you will see. So we started with the vacuum tubes, then comes the transistors. Then first point contact and junction transistors we have seen. Then comes the concept of integration, integrated circuits. So that time it was less than 10 or hundreds of transistors called as LSI. Then comes LSI stands for large scale integration. Hope you know it. Then comes VLSI, very large scale integration, and now we may treat the technology reaches at ULSI, ultra large scale integration, where there are billions of transistors are present in a single chip. Okay. So the power considerations and the packing density, speed, all these factors are given due consideration while you scale the technology. Okay. While the technology scaling is considered, all these factors are very important, as shown in the last column. Hope most of you know about the basic MOSFET structure and working. So, you know, it consists of, as the name indicates, it's semiconductor. FET means field effect transistor. So, as per the name, there is a metal region at the top, then outside region, then at the bottom. Actually, I should start from the bottom, I think, because fabrication starts with the substrate, wafer region. Okay. So at the bottom there is silicon substrate, and there are two highly doped regions, source and drain regions. Okay. Source is the source of carriers, and drain region is where the carriers are finally draining into. So as per the gate voltage you are applying to the device, you know, a channel region will be formed between source and drain, right? Should I tell the detailed working? So all of you know the basic working of device. Then at a particular gate voltage, you know, the channel will be formed between source and drain, that is actually an inverted channel. So if the substrate is originally p-type as shown here, the channel formed will be of which type it will be? It will be n-type channel. That is what is called as an inverted channel. And then if you apply the drain voltage, it enables the carrier flow between or from source to drain. So here you can see the gate is aligned on top of a silicon dioxide region, and as far as possible the overlap between gate and source, also between gate and drain, that overlap should be reduced. Okay, if there is much of overlap between those regions, then gate capacitance, gate to source and gate to drain capacitance will be more. That may slow down the device. Okay. And regarding the source and drain regions, whichever is at a lower potential, that is treated as source, and the region at higher potential is treated as drain. And the dimensions, the main important dimensions of the MOSFET are length of the channel between source and drain, and width of the channel. This is clear from this 3D figure. So in earlier days, the gate region, it was of metallic gate, but there are some problems with the metallic gate. As highlighted here, there are two important reasons for giving the transition to polysilicon gate. One point is that, as I mentioned earlier, there are two overlap capacitance shown here between gate and source and between gate and drain. So, if the metal gate is misaligned, there are more chances of misaligning the gate during the fabrication. Okay, so if misalignment happens, as I told you earlier, these two overlap capacitance will be more in value. That may slow down the device. Okay, so that's why there is one more reason for changing the metallic material. You might have heard of ion implantation, right? To create the source and drain regions, the dopants are to be implanted to the corresponding regions. So during ion implantation, a very high temperature is used, greater than 800 degrees Celsius or so. So that much high temperature may melt down the metal. So if you adopt polysilicon, the melting point of aluminum, metallic material, generally comes in this range, but the ion implantation uses very high temperatures. Okay, so that is not at all desirable for the gate material. So instead, if polysilicon is used, it would not melt during the ion implantation, and also an annealing step should follow the ion implantation. That also deals with higher than lower temperatures. Then there is one more reason actually. The threshold voltage, the equation you might have studied in maybe solid state devices course. The equation for threshold voltage. So it actually, there is a term containing the metal to semiconductor work function, phi ms you may call it. So the phi ms decides threshold voltage. That is one factor. So if you use a polysilicon gate, then you can easily adjust the threshold voltage by twinning this term of phi ms, work function between gate and the semiconductor. Okay, that is one more advantage of using the polysilicon gate. Then working principle I had just mentioned, that is basically with the inverted channel region. The P substrate, when you apply positive gate voltage, the P substrate, some portion will be depleted, depletion region will be present, and even if you increase the gate voltage, again if you increase, then electrons will be attracted to the surface of the semiconductor. So, forming an inverted channel, Okay, so through this channel region, the carriers can make a flow between, when you apply a drain voltage, carriers will make a flow from source to drain region. That's the basic working principle. So that inversion region as well as depletion regions are shown here. Depletion region, you know, it contains immobile ions. Then the inverted channel consists of, here it is negatively charged particles. Electrons will be there in the inverted channel. And this is one simulation done using Centaurus simulator, device simulator. It's a commercially available device simulator. Here you can see the electric fields, one-dimensional fields plotted. Here red color indicates, sorry that light is missing. I think the value is around 10⁻³ volt per centimeter or so in the red region, that is having the highest electric fields. So actually the fields are controlled by gate voltage. So you can treat that as a vertical or transverse electric fields across the device. So the current flow is controlled by the gate field, okay, and also by the drain voltage. So this you can treat as a long channel device. Long channel in the sense the channel length will be higher than the combined width of drain and source depletion regions. So for long channel devices, the gate field will be mainly controlling the inverted channel. But if L is small, what happens if L is small? That means short channel device, the length will be comparable to the combined depletion width of source and drain region. In that case, what happens? The channel is controlled by not only by the vertical electric field or transverse electric field, it is also controlled by the lateral electric field provided by drain voltage. Okay, so drain is also gaining an upper hand on the channel current flow when the device is getting smaller. So why should we deal with short channel devices? Because as the technology is scaling down, these length and depletion widths, they are becoming very much comparable. Okay, so how to do the device engineering with short channel devices, that we should know. So the observations are like this. The field is no more one-dimensional because there are vertical as well as lateral electric fields coming into the picture. Then short channel effects are the reason gate loses control over the channel. So technology scaling, we need to make the devices fabricated with lesser area footprint, then low power consumption, obviously at a lower cost. So the requirement, most of your smart devices battery requirement, that's also going high, right? So for portable devices, the power consumption, especially as that is scaling down, the power dissipation is an important factor. Okay, because how much standby power can be given, the power design becomes an important criteria for short channel devices and also for the smart devices there. Also, when the transistors are getting smaller, the capacitance would come down. So that leads to, as I told you, capacitance is related with the speed of the device. Delays will be reduced. Okay, and dynamic power is also proportional to the capacitance. You may know the formula for dynamic power, right? So it is actually CV²F. So capacitance is present there as well. Power consumption reduces. So this reduction of transistor size is called scaling. Okay. So when the first microprocessor was invented in 1971, It was actually utilizing a 10 micrometer technology node. Okay, 10 micrometer is the feature size in the first node. But as the technology is scaled down, then progressed on to 1 micrometers, then 0.18, 0.13, 90 nanometers, etc. These are various technology nodes. In between, half nodes may also come in, dictated by Moore's law. So, in shorter devices, the edge effects are coming into the picture. For long channel devices, the edge effects could be negligible. But in short channel devices, the electric fields are influencing the channel from all the sides. Influence of drain electric fields also coming into the picture, as I told you before. And definition of short channel device is given here once again. If the channel length is not much larger than sum of source and drain depletion width, then this is called as a short channel node. Okay. So now let us quickly look into the issues faced by short channel nodes. One is the gate leakage. That is, you can see when you apply the gate voltage, in a short channel node, the intended current flow is from source to drain only. But the carriers may also, due to the high electric fields, some of the carriers may also penetrate into the gate. That is actually called by some hot carrier effects. We will see that. Also, the channel is supposed to conduct only when the gate voltage is above the threshold voltage. But even below the threshold voltage, there is some small leakage current. It is called as subthreshold conduction. Okay, so that is one undesirable short channel effect. So what we need is, in a device, the on current should be high and the leakage current should be minimized, so that the on current to off current ratio should be maximized. Okay, that is one important figure of merit, I on to I off ratio, that we will look into while we do the device design or simulations. And these are the summary of short channel effects: gate leakage, velocity saturation, then dipple, drain induced barrier lowering, subthreshold swing. These are some of the short channel effects, major short channel effects. So velocity saturation, you might know, actually the drift velocity of the carriers, it is proportional to the electric field. Especially for lower electric field value, as shown here, drift velocity V is given by mobility times the electric field. And for short channel devices, the velocity is found to be saturating at a critical electric field. It's around 10 raised to 4 volt per centimeter. Then what happens? The velocity tends to attain a saturated value. Okay. What is happening physically is, due to the high electric field felt by the channel carriers, the carriers will scatter off at the oxide interface. Okay, gate oxide to channel interface. So the carrier mobility may come down. Okay, so that will lead to a saturated value of velocity and also a lower value of drain current. Okay, most of you might have studied this, right? Then another effect is dipple, drain induced barrier lowering. When you apply drain voltage, as the drain voltage increases for short channel nodes, the barrier from source to channel barrier felt by the carriers, that will come down. Okay, so what will be happening finally? Ultimately, it will lead to the reduction of, what will happen? The reduction of threshold voltages. Okay, that is also causing subthreshold currents. Okay, the channel will conduct at a earlier gate voltage, a very low gate voltage. So that is totally undesirable, drain-induced barrier lowering. It is found in short channel nodes. So what is happening is the channel charge for long channel device is proportional to W into L. W is the channel width, L is the channel length. For short channel device, the channel charges are equally held by gate as well as drain fields, drain voltages. Okay. And through DP, we have seen that the threshold voltage is reduced compared to a long channel device. And you know the threshold voltage equation that is given by flat band voltage, summation of flat band voltage, the Fermi potential, then the depletion layer charges, QD by Cox. This is the formula for threshold voltage. And for short channel device, you can see there is an extra factor. Okay, RJ, this geometry RJ and XD max is shown in the earlier figure. Okay, this is given by the radius of this span of this region. Then XD is the width of the depletion region. So, for short channel nodes, there can be a change in the threshold voltage given by this extra QD by C of this factor. Okay, so there can be threshold voltage variations due to instability in the channel parameters. Another important parameter as far as short channel nodes are concerned is subthreshold swing. Okay, this equation is given here. dVGS by d log ID. So it actually measures how much change is there in the subthreshold current when you give how much decade change in the current when you give the gate voltage. Okay, actually this is measured in the subthreshold region, subthreshold swing. Generally, it is found as some 70 millivolt per decade. But for short channel devices, S is found to be higher unless some measures are adopted. Okay, it is desirable for having a smaller S. Smaller the value of S, the better the device can be controlled in the subthreshold region. Okay. So if S value is higher, the leakage current, the off-state current will also be higher. Another major effect you might know that is called as punch through. Because when you increase the drain voltage, what happens? The depletion region, the boundary of depletion region is indicated like this through dashed lines. The depletion region in both the sides will come together. So there will be uncontrolled path for the carriers. Okay, this is called as punch through effect. So once punch through happens, the device becomes useless. So actually there are preventive measures for each of them through device engineering. You may do some anti-punch through implants and can give lightly doped drain regions. Okay, doping is controlled. Slightly doped drain near the drain region. And also you may use high value of the dielectric material can be chosen in such a way that the dielectric constant is higher. The final purpose is to have a better control of gate over the channel. So for that, various device engineering measures can be adopted. So these are some of the measures. The channel doping concentration can be increased, or the gate capacitance can be increased. Okay, all this leads to a better control of gate over the channel, or you can adopt the strained silicon technology. That means silicon deposited on top of silicon germanium material, or you can use a high K dielectric, or even a smaller gate oxide, but actually the thickness of gate oxide and all is given by that particular technology node. Cannot be reduced so much. There are certain rules for choosing the device geometry given by the technology nodes. Also, there is another problem in polysilicon called as polydepletion. In order to eliminate polydepletion, you may have to go back to metallic gates. Okay. So the gate oxide, the capacitance is given by oxide capacitance is given by Cox. This is actually epsilon Ox divided by Tox. So here using this equation you can see the capacitance can be reduced if you increase the Tox, or if the physical oxide thickness is increased, then capacitance can be reduced. And there is another rule of thumb, the relation between the channel length and Tox. It is actually, this is applicable for a particular technology node given by Intel's technology. L is equal to 45 into Tox. So L, Tox, everything is given by a particular technology node backbone. Okay. So I had mentioned about mobility degradation caused by the various short channel effects. So in order to improve the mobility value, one method is to use the strained silicon technology. That means actually silicon deposition is done on top of SiGe layers. Okay, so the top silicon thin film will try to adjust with the underlying silicon germanium layers. So it will look like a strain layers. The lattice position will be adjusted in such a way. So the lattice constant of silicon and silicon germanium will be adjusted. So the advantage is that this particular technology results in an improvement in the mobility. Actually, this method is adopted even in latest nodes, strained silicon technology. Even the latest FDP devices used in the latest iPhones and all, those transistors use this particular strained silicon technology. There is another important term called as effective oxide thickness. So what happens is, if the oxide thickness comes below this effective value, effective oxide thickness, then the gate leakage will increase so much. So for example, if you take hafnium dioxide, HFO2, a 6 nanometer thickness layer if you choose, then the effective oxide thickness will be 1 nanometer. Okay, so if you choose a higher K value, dielectric constant value, then that means you can actually reduce the effective thickness value. Okay. And you can see the thickness limit for the oxide is approximately 1.6 nanometer. It is set by other undesirable effects such as gate tunneling, quantum mechanical tunneling and all. And actually this thickness is fixed by the, as I mentioned earlier, the technology node. The rules should be followed. And for polysilicon also, if you choose as gate material, there is one undesirable effect called as polydepletion, which I had mentioned before. There can be, polygates can become incompatible with the high K dielectric in some cases. In that case, the depletion comes, so you may have to change the high K oxides. And considering all these short channel effects, there are several device changes, several technology improvements have been considered, not only in the device structure but also in the material level. Novel materials are adopted, including the carbon nanotubes and all, nanosheets. then other compound semiconductors to achieve improvement in mobility and device speeds. Material engineering, that is actually has a huge role to play. Then device optimization. Actually, this electrostatic integrity, that's actually it's a vast topic. The electrostatic integrity measures can be adopted, and in every device design, there is a particular parameter, electrostatic integrator, given by lambda, and that value is always checked whether that integrity measures are met or not. Then, as you have seen earlier, strain improvements can be done. Then in the architecture level, device architecture area also, several different geometries are experimented, and as per the technology scales down, the device geometry itself is changing. Then also there are another phenomena in the magnetic resistive memories. You might have heard of magnetic memories, phase change material. All these are other areas of research where you can improve the device performance. So, considering the short channel effects, and in order to improve the control of gate, there are several device variations are considered. One such structure is SOI, silicon non-insulator. SOI structure, that is another FET geometry, SOI, silicon non-insulator, that has actually that has brought several improvements could be introduced through this SOI, silicon non-insulator technology. Also, you might have heard of FinFETs, where the channel, it is actually having a fin-shaped channel. Have you heard of FinFETs? It's there in syllabus. So the objective of alternative structures is that the gate to channel capacitance can be maximized, and the drain to channel capacitance can be minimized. Okay, the control of gate over the channel should be maximized. That's why it is shown as gate to channel capacitance should be maximized. Okay, that's why we mentioned high K materials before, so that the effective oxide thickness can be reduced, so that the gate has a better control over the channel. So when SOI wafer is shown here, you can see a buried oxide layer here deposited on top of a base silicon wafer, and on top of that thin film silicon will be deposited, which actually forms the channel and functional layers in the FETs. This buried oxide layer can actually reduce the parasitic capacitance to a large extent. And you also might have heard of latch-up effects in short channel nodes, especially that happens in normal CMOS configurations. If you use a twin-tub technology, twin-tub fabrication process, okay, there are parasitic BJTs forming a positive feedback connection. Okay, so that results in leakage currents in the CMOS geometry. Okay, so such latch-up conditions can be avoided completely if you use an SOI kind of wafer. So actually we are fabricating the device based on this SOI, silicon non-insulator wafers. So the three layers are listed here. The base layer is also called as a handle wafer layer. Buried oxide layer is what is shown here as BOX layer. So these are the advantages of such a SOI structure. The junction capacitance can be reduced, latch-up will be eliminated, and another advantage is that when you scale down the device, the thickness of buried oxide that needs not be changed. Okay, that is another advantage. Then conventional, compatible with the silicon processing standard techniques. Then these points are mentioned before. Reduce leakage. Okay, error rate can be reduced. Also, power consumption, threshold voltage control, all these are given to this SOI technology. But there are certain drawbacks as well. Have you heard of kink effect? Kink effect in FET structures. So, actually, you can see here the channel region or the body region seems kind of trapped between oxide and buried oxide, isn't it? See the body region here. So maybe some carriers under the high electric field may get acquire very high kinetic energy in this region. Okay, so for a high drain voltage, when you increase the applied drain voltage, the current may rise at a faster pace at higher drain voltages. Okay, that is totally undesirable. The current may go out of control. That is called as kink effect. Drain current overshoot might happen. That is one major drawback of SOI technology. Then thickness control, as I mentioned before, the buried oxide thickness that won't be scaled down. Then due to the trap states here, there can be surface states happening. Due to the same reason, it suffers from history effects. The previously trapped charges may affect the device operation. And self-heating. Due to trap charges, self-heating might also happen in SOI technology. So there is some fabrication difficulties as well in manufacturing thin body SOI cables. Advantages are again listed down here. You can just go through the advantages. Mainly it improves the speed by reducing the parasitic capacitance. Okay. And latcher problem is eliminated. Here that parasitic BJTs are shown. Here from the end well, this BJT, you can see the base of one BJT is connected to the conductor of the other BJT. Similarly, base of this BJT is connected to conductor of the other parasitic. All these are parasitics. So this positive feedback connection causes a latcher problem. Device may fail to work, but in SOI CMOS technology, if you see here, there is no possibility of forming that BJT, formation of BJTs, parasitic BJTs, that is, possibility is eliminated here. Then these SOI devices are in various types. One is PDSOI, that is partially depleted SOI MOSFET. Actually, PDSOI is having more of such problems. Kink effect, as I mentioned before. Kink effect, history effect, and also self-heating problems. All these very much affect the partially depleted SOI. Why it is called partially depleted? You can see the floating body here, right? So, in fully depleted device, this body region is very thin. The entire body region is fully depleted. And you can see it is called as ultra thin body. Fully depleted. FD means fully depleted. And body is very thin, of the order of 5 to 20 nanometers. But PDSOI, there are still neutral regions in the body. It's only partially depleted. PDSOI. And if you use FDSOI technology, to some extent, such kink effects, such disadvantages of PDSOI can be eliminated. So those two technologies have been compared here, PDSOI and FDSOI. here the buried oxide thickness, it is larger compared to FDSOI. Here it is only 550 nanometer, or maybe even less than 20 nanometers. And these are especially sought after in low power applications. Actually, these technologies were invented around 1990s. From that time onwards, these technologies are in existence. Okay. So, as I told you before, you can call it as ultra thin body, this yellow region. So, here you may not have much constraints on the TOX. There are some relaxations while you design the gate oxide thickness and all. Another one is double gate MOSFET. So here you can see the channel is surrounded by two gates in two directions. So obviously the channel will be having a better gate control, isn't it? But fabrication wise, such a structure is somewhat difficult because underneath that thin body you have to pattern this gate region. Okay. So this actually not used much due to that fabrication complexity. Though it has various advantages such as better control of short channel effects, lower threshold voltage and all. Mobility can also be improved. But practically this could not go much into the technology notes. There comes another invention such as FinFET, overriding double gate technology and all. Because in FinFET structure, you can see the gate is surrounding, it's like a tri-gate, right? If you have some insulator layer here, actually if you give some spacer layer here, then it's similar to double gate. That's why it's written as double gate or FinFET. Okay. For the region to function as gate, there should be an oxide layer, and on top of that the gate material should be deposited and patterned. So tri-gate FinFET is having control over the channel from three sides. Similarly, there are ohmic gate, quadruple gate. But fabrication wise, this is very difficult, quadruple gate. So actually all these double gate or FinFETs advantages are listed out here. Scalability, low junction capacitance. Actually all these gates are very much self-aligned. All these comes under self-aligned gate technology. That means first after patterning that thin body layer, you are depositing the oxide material, gate material and all. First the gate portion is done first. Only after that the drain and source implantation is done. So the gate region itself acts as a mask for depositing drain and source regions. That's why this is called as a self-aligned gate technology. Okay. So this is the basic explanation of FinFETs. Actually, this came into existence after 2010. TSMC, Taiwan Semiconductor Manufacturing Company, TSMC, the structure was used even before 2000 this year, but the structure got commercialized with Intel's, I think it is 22 nanometer technology. With that Intel's technology node, this FinFET came more into the marketing side, enjoys the chip side. So here you can see for the FinFETs, the body, this thin body, it's very thin, around 10 nanometer or less. It's actually, the gate is surrounding the body. This orange region is the oxide region, and the body is shaped like a fin. you can see the channel width here. Then channel width is not only given by this portion. What is the effective channel width? Because gauge is surrounding from 3 sides, right? So the effective channel width will be, you can see one fin width here. Fin means that small thin body portion. Okay. So it's called fin because the silicon body resembles the back fin of a fish. That's why the name fin fet. The effective channel length you can treat like twice this fin height plus fin width, because gauge is covering the channel from those 3 sides. So the effective width of the channel is given here. Width of the channel is 2 into fin height plus fin width. Okay, 2 times fin height plus fin width. So both 2D traditional planar technology and the 3D, this is planar MOSFET, this is FinFET technology, both are compared here. This FinFET technology is having very little leakage due to various reasons, due to the better control of gauge. Then there are much improvements in power as well. So it is treated as a very important innovation, significant innovation in the device nodes. Okay. Actually, it came into existence along with the 20 nanometer technology nodes. Unlike the conventional 2D structure, this is a 3D structure. Like the gauge is surrounding the channel over the 3 sides of the channel through the fin-shaped body. You might have heard of ECE processors. Since 2018, the FinFET has been much used with this processor design, and Samsung could utilize this FinFET nodes in its Exynos 9 series. Okay. It is actually utilizing a 10 nanometer FinFET technology node. And even in today's 7 nanometer and even in 5 nanometer nodes, FinFETs are used, but not beyond 5 nanometer. Coming down to 5 and 3 nanometers. Okay, 5 nanometer, 3 nanometer nodes, they are actually utilizing even an advanced version of FET structures, not FinFET. So these are the different types of FinFETs based on the geometry of the gate. Triple gate, omega gate. Omega gate was shown before in one of the figures. Then nanowires. In some cases, the gauge is patterned as nano sheets. Not gauge, the body is patterned as nano sheets. Then high K FinFET, strain FinFET. Strain technology, as I told you before, strain technology can be used in this FinFET and the advanced nodes. So based on the geometry of this fin, again there are tall FinFET, short FinFETs, also nanowire FinFETs. Comparing these 3 structures, this short FinFET will be easier to fabricate because there is it is less challenging as far as the lithography, other processing steps are concerned. Nanowire FET, they have even better control of the channel region. Because you can see the gauges surrounding that nanowire shaped thin body. Okay. can see just a geometric view how the double gate FET can be converted to a FinFET. I mean, here you know the gauge is only on the two sides of the channel, and if you give a continuous control along the channel, it's like this three tri-gauge structure. So what I meant to tell you is that the layout is similar. Okay. And in triple gate FETs compared to double gate FETs, here the drain currents have been found to be increased, 20% increase in the drain currents. Here width of the silicon, width of the channel. There's a rule of thumb in many of the technology notes how the width and length are related. Okay. Width W and how they are related, which is also shown here. And nowadays it is not a single fin. Actually, multiple fins are patterned over the same substrate like this. So what happens? The effective channel width can be improved in such cases. It's like multiple nano sheets patterned under a similar uniform gate material. And here also one TEM image of 10 nanometer node is shown. Also the CARA, ID versus VG transfer CARA is shown here for 5 nanometer and 10 nanometer nodes. Fin width is comparable with twice the gate length, 2 LG. And leakage paths can be there, but still compared to the other SOI technology, the leakage current is minimized. So these are some of the advantages of multiple gate transistors. Better control, reduce short channel effects, and scalability, subthreshold current, etc. So the off current can be minimized. At the same time, on current is also improved. Okay. Actually, a comparison is given in the following slides between the conventional and the latest technology nodes. What's the break? And subthreshold slope also, you might remember subthreshold slope, it is given by dVg by d log ITS. That means it's the derivative of gate voltage as a decade factor of the subthreshold drain currents. Okay, so it's better to have very low subthreshold swing, less than 60 millivolt per decade. Okay, so very lesser values actually desirable. So if you go for such advanced FET structures, to some extent you can ensure that the subthreshold swing both are actually opposite. Subthreshold swing is there, also subthreshold slope is there. Okay, so the slope value of less than 60 millivolt per decade, that much better control of currents you will get. Okay, so that is how much decade change in the drain current when you increase the gate voltage, maybe by 1 unit. Okay, so that value should be as low as possible. And we can see better the patterning of this electric field. Better they are aligned, we will get improved control of short channel effects. So in double gate you can see they can electrically shield the channel double gates. But here there is limitation as far as this electric field patterning is considered. These were shown before, double gauge structure, omega FinFET, and here the channel is actually narrow wire shape. See, the research on such FinFETs, they are, see, this is 5 nanometer, 8 nanometer FinFET. These figures are taken from this conference paper. Research are the right from, I think, 2011. But the commercially available nodes came into existence from 2018, that year onwards. Maybe from 2011, by the Intel's FinFET node. It was out commercially in 2011. So actually there is a gap between the research and the actual realization of such devices, especially the very advanced FET geometries that I will deal with in the coming slides. Process flow is shown here. First, as I told you, you have to pattern this body region. The silicon fin is patterned here. Then the gate region is deposited, polygate deposition, and it is patterned using EUV, extreme ultraviolet electron beam lithography techniques. Then also you need to give some gate spaces, because there should be some gap between gate and source and drain regions. So gate spacers are needed. So spacer deposition is also done here. Some insulator you can choose as gate spacer material. Then comes the source and drain region implantation. And after implantation, it should be followed by an annealing process and also a silicidation process. You can just go through the advantages of FinFET in terms of the control on short channel fix and the mobility of the carriers, performance wise. Then both this SY technology which I had shown you before and the FinFET, actually they are having, the common characteristic is that they are having a thin body region. And as mentioned in the last point, FinFET technology provides numerous advantages in terms of the on current, speed, and the off-state current or leakage current, power consumption, and dopant fluctuation, etc. So actually, beyond 22 practically it is 22, beyond 22 nanometers, then 10 nanometers, 7 nanometers, and even at 5 nanometer nodes, FinFETs are used. Starting from 5 nanometer and beyond, another alternate structures are coming up. Okay. That we will see, I think, after the break. There are some more alternate structures which were introduced after FinFET. Okay.
അപ്പോൾ നമുക്ക് ഫീഡ്ബാക്ക് കാണാൻ മൂന്നേ അച്ഛനെ തിരിച്ചെത്തേണ്ടതാണ്.
പക്ഷേ അത് ഒരു സർക്യൂട്ടിൽ വേണമെങ്കിൽ നമുക്ക് കൂട്ടാം. കാരണം വെച്ചാൽ അതിന്റെ പാർട്ടിന്റെ കൂടെ നോക്കിയൊക്കെ ചെയ്താൽ അല്ലാതെ ഒരു ഇലക്ട്രോണിന്റെ സ്പൂൺ കൂട്ടാൻ നോക്കിയാൽ എന്റെ ചോദ്യം ആ സാധനത്തിലല്ല, അതിൽ എനിക്ക് ക്വസ്റ്റ്യൻ ഉണ്ട്. അത് ഞാൻ ചോദിക്കാൻ വെച്ചിരുന്ന സബ്സ്ക്രൈബ് ആണല്ലോ അതിനകത്ത് തുറന്ന ഇലക്ട്രോണിനെ മാത്രമേ ഉപയോഗിക്കാൻ പറ്റും എന്ന് പറഞ്ഞാൽ അപ്പോൾ അതിന്റെ ക്യാരിങ് കപ്പാസിറ്റി കുറവ്, മൊത്തം ഇലക്ട്രോണിന്റെ എണ്ണം കുറവ്. പിന്നെ ഈ താഴത്തെ പോയിട്ട് എന്ത് വെച്ചിരിക്കും? അവസാന ക്വസ്റ്റ്യൻ ഉണ്ടോ ചോദിക്കാം.
ഓക്കെ ഓക്കെ ശരി. ഇന്ന് ചെയ്തതാ ഒ ടി പി വരുമോ? ഒ ടി പി വരും ചേട്ടാ. വരുവാണെങ്കിൽ നിങ്ങൾ വിളിച്ചാൽ മതി, ഞാൻ തരാം. വരുവാണെങ്കിൽ വിളിച്ചാൽ മതി, ഞാൻ തരാം. തോന്നുന്നു ഇവിടെ എന്തോ വലിയ സൗണ്ട് കേട്ടുകൊണ്ടേയിരിക്കുന്നുണ്ടല്ലോ. അറിയില്ല, ഒരു നല്ല ഡീപ് സൗണ്ട്, ഭയങ്കര നല്ല സൗണ്ട് ആയിട്ടുണ്ട്. എന്തോ വരെയാവോ അച്ഛൻ്റെ മൈക്ക് മറ്റേ ആംബിയർ ഒക്കെ ഇരിക്കുന്ന സ്ഥലത്തിൻ്റെ അടുത്താണ്. നല്ല സൗണ്ട് ഉണ്ട്, ഭയങ്കര സൗണ്ടാണ്. വരാൻ പറ്റുമോ? എന്താ ഒന്ന് ഇറങ്ങി വരാൻ വന്നോ? ഭയങ്കര സൗണ്ടാ. ആ മാം കുഴപ്പമില്ല, പറഞ്ഞോ മാം, തിരക്കാണ്. അതെ, അറിയാം. മാനേജ്മെന്റിലാണോ മാം പറയുന്നത്? അവരെ ഹോൾഡിൽ വെക്കുന്നതായിരിക്കും നല്ലത് ഇപ്പൊ കറന്റ്ലി, കേട്ടാ. ഇല്ലാന്ന് പറയണ്ട, അലോട്ട്മെന്റ് വരുമല്ലോ, അലോട്ട്മെന്റ് കയറി വരാൻ പോസിബിലിറ്റി ഉണ്ട് മൂവിയിൽ. അതെ, അതുകൊണ്ട് അത് അപ്ലിക്കേഷൻ തന്നു വയ്ക്കട്ടെ, ഞങ്ങൾ പറഞ്ഞിട്ടില്ല. ഓക്കെ ഓക്കെ ഓക്കെ.
അഞ്ച് മിനിറ്റ് കൂടി ഓടാൻ പറ്റുമോ? അവിടെ എത്താൻ പറ്റുമോ? പോയി
So let us assume. So in the previous session, we had seen starting from the conventional MOSFET structure. We had discussed a few short channel effects. There we understood the need for alternate definitive structures, right? Then we have seen the SOI technologies, both the partially depleted PDSOI and FDSOI technologies. Also, there we could see using that thin body, thin silicon fin itself, if you use multiple gates, we can have a better control of channel or gate drain currents, right? So, thereby controlling the short channel effects. So, double gate MOSFET didn't become so practical fabrication wise. So, there came the advanced versions such as FinFET. So, starting from 2011 with the 22 nanometer technology, the nodes changed to FinFETs. And Intel, Samsung, everyone switched to this FinFET nodes for further IC fabrication. And we also discussed various advantages and also difficulties associated with some of the FinFET types. Due to some scalability issues, beyond 5 nanometer technology, FinFET couldn't be adopted. So at very recent nodes, the technology again changed to one another in this also we had discussed SOI versus FinFET, because SOI technology and FinFET technology we have seen. If you compare both of them, let me come to the very advanced technology after this. Okay? If you compare SOI and FinFET, you know the SOI fabrication wise, FDSOI is offering lot of advantages, and also there are not much undesirable effects in FDSOI technology. Then in FDSOI you can also apply, there is one more point with FDSOI technology, you can apply a backgate bias. In addition to the gate bias, a backgate bias can also be applied for better control of the threshold voltage. That is possible. But the problem is that the number of SOI wafer suppliers are less in number, because you have seen that there is a buried oxide layer on top of the base silicon layer. Okay. So buried oxide, as per the technology scaling, there are not much scaling options available for the VOX layer. So that is one disadvantage. Then obviously the very high cost of silicon, SOI silicon wafers. That is one disadvantage of SOI technology. Then coming to FinFET, you have seen that the continuous gate wrapping around the channel. There is very good control of channel, as well as you can expect high drain currents around the channel. Then in the advanced nodes beyond 7 nanometer, strain engineering is adopted. That is silicon on SiGe layer. Okay, that strain engineering is done to improve the, do you remember what's the advantage of that strain engineering? That is to improve the mobility. Okay, the top silicon and lattice position will adjust with the bottom SiGe thin layers. Okay, so improved mobility we can have. That option is there in FinFET nodes. But the problem is that if you try with the omega or quad gate type of FinFET, then it's a bit difficult to pattern the gates. Okay, through litho it is difficult. When if you use extreme UV lithography. Okay. So obviously what should be the next technology after FinFET. Okay. Below 10 nanometer nodes, actually in 7 nanometer also FinFETs are still used. 7 nanometer we use in the technology, chips are available still now. I have told before in the latest Apple iPhone 16, there is one A18 Bionic processor is used. That A18 Bionic chip, the technology is 4 nanometer. And in its higher nodes, maybe iPhone 15 also, I think even before that, in iPhone series itself, recent node, it is 5 nanometer FinFET. But in the latest 4 nanometer nodes, they are using the other advanced option, not FinFETs. The major another disadvantage along with the points previously mentioned, it is less efficient in terms of heat dissipation. Because you have seen that the fins are very thin, of the order of 5 to 10 nanometers. So with these very thin fins, it is difficult to accommodate the heat generated. So that's one important disadvantage. So there should be some new class of design rules, design for thermal, design for manufacturability. These factors also need to be considered for the advanced nodes. So there are carbon nanotube FETs, but they are still in the research phase. CNT FET I had mentioned before. The fins, silicon fins, instead of silicon fin, we can go for carbon nanotubes. They have not been marketed, but this option, that is gate-all-around nanowire FET, there the body, thin body is patterned as nanowires. Okay, so that is the another ongoing invention, gate-all-around nanowire FET. This is also called as gate-all-around FET. That is shown here, gate-all-around nanowire FET. That is the latest trend. So I had mentioned there is one another important parameter called electrostatic integrity, which is related to the length of the channel, natural length of the channel. So actually this natural length, it is not the physical length. Natural length lambda, it represents the length of the channel that is controlled by the drain. That is significant for short channel nodes. Okay, so this short channel effects can be suppressed if gate length is larger than 5 to 10 times, 5 to 10 times this natural length lambda. And why I should mention lambda? Because lambda is very much essential, very much an important parameter in the electrostatic integrity based design. Okay, nowadays this electrostatic integrity, that is sought after in the device engineering. Okay, so the lambda is considered based on the lambda value. This EI, electrostatic integrity short form is EI for the designs, where EI value should be as low as possible. That is one another major parameter along with power, area, delay considerations. Okay. So first we have seen single gate structure, then double gate, then FinFET, various geometry we have seen, and now the trend is to change to gate-all-around nanowire FET. So this is the gate-all-around MOSFET, cylindrical device it is. Both rectangular and cylindrical options are available. The figure shows a cylindrical structure. So you can see here the body, the thin body, it is patterned as a nanowire. On top of that you can see the oxide and the gate material. Okay, so initially that thin nanowires or even nano sheets can be used. They are patterned first. They are actually stacked like an array. There are this single device മാത്രമാണ്. But actually fabrication ചെയ്യുമ്പോൾ there are an array of stacks of devices. അപ്പോൾ ആദ്യം എല്ലാ ഫിൻസും പാറ്റേൺ ചെയ്തതിന് ശേഷം then you have to do the lithography for the gate oxide deposition, then comes the gate patterning. Okay. Then as I mentioned before, after gate patterning you have to deposit the sideboard spacers. Finally it is followed by source and drain implantation. So it has now come into the market, the gate all around FET structure. It is first used by Samsung in its 3 nanometer process node, technology node. So Samsung thus has become the first ever foundry to use gate all around FET. It also uses this multi-bridge channel FET, another small variant of this. It is the proprietary version of gate all around FET. They are used in, nowadays AI machine learning is very much on the emerging side. So for AI computing devices, AI chips, high performance computing and all, this technology node is very much highly preferred. Okay. Then another upcoming node, this is not yet into the market, but it is expected to be soon in the market. Upcoming 2 nanometer node by Taiwan Semiconductor Manufacturing Company, TSMC. It is expected to be out by the end of this year. So all these technology, especially AI-based accelerometers and all, they are shifting to gate all around devices, processors based on such latest version of transistors. This is a comparison between various FETs, double gate, quadruple, cylindrical gate. Cylindrical gate mainly comes in this gate all around FET category. So you can see that the threshold voltage, actually this is not exactly the same nanometer. I think this is in the 10 nanometer, this is 1007. Sorry, that is not mentioned here. And this is in the 3 nanometer category. Okay, this is based on the simulation results. Simulation done in Centaurus simulator. So threshold voltage is found to be slightly different, but what you can infer from this is the ion, the drain current, that is improved in the cylindrical FET geometry, that is gate all around effect. The on current is higher, similarly off current is very lower compared to double or quadruple gates. So I had told you this is an important figure of merit, on current to off current ratio, that you can see as around 10 times improvement in cylindrical gate structure, gate all around FET. Then subthreshold swing, how much gate voltage change is required for a decade change in the drain current. That is what is mentioned or indicated by SS, subthreshold swing. So you can see the cylindrical as well as quadruple gate, they are offering a very much improved value of subthreshold swing, SS. That means, what does that mean? The gate has even better control on the channel. Okay, so smaller the value of subthreshold swing, better the control of gate, especially in off state condition. Okay. Then transconductance value also you can see improvement in the case of cylindrical and quadruple gates, and the improved value is there for on current, off current, transconductance, subthreshold swing, and also this is the Dibble parameter, drain induced barrier lowering. That means the change in threshold voltage per unit change in the drain voltage. Okay, that is the Dibble parameter. So you can see that change in threshold voltage is also lower for the gate all around device. So as a whole you can see there are very much performance improvements offered by the gate all around device. quadruple cylindrical gauge FET performance-wise, there is not much of a difference, but still there are improvements for cylindrical gauge structure. And quadruple gauge, I had shown you one omega gauge device before. And there are some corner gates better. At the corners, you can see that shape change. So that's why they build. It is large for the quadruple gauge. Then another important innovation in the device, semiconductor devices, tunnel field effect transistor, TFET. But sadly to say, this is not in the practical terms yet. This is still in the research. Okay. The advantage of tunnel FET is that this works on the basis of quantum mechanical tunneling along the channel region. So here the band diagram is shown. You can see this is for the general MOSFET. Let me take the band diagram for a tunnel FET. Here the structure-wise difference is that for MOSFET, you know, both source and drain will be either N plus or P plus down, same topic. But for tunnel FET, the source will be P plus, then the drain will be N plus. Okay, and when the major carriers are electrons. Okay, so from here, drain, channel, source regions are shown here in the energy band diagram. You can see there is a tunneling region from the source to channel. This is the tunneling junction. You know, electrons start its journey from source, isn't it? So there is a tunneling junction from source to the channel region modulated by the gate bias. Okay. So due to this quantum mechanical tunneling involved as its main working principle, the major advantage is that in tunnel FET, the off-state current, the leakage current is around 10 to 50 times smaller than other gate-all-around or other conventional FET structures. Okay, the improvement in this off-state current, that is the major advantage for tunnel FET. Here, all this in the conventional structure, you know, the basic working that's based on thermionic principle, but whereas in tunnel FET it is quantum mechanical tunneling. So this is the structure of tunnel FET. Here we can see the body region that is not P or N type, that is instead an intrinsic region. And source is P plus, drain N plus for electrons as the carriers, N type tunnel FET. At zero gate voltage, this is the working given briefly. At zero gate voltage, there is large barrier for both the thermionic emission. As I had told you, thermionic emission is the only mode of carrier injection for MOSFET, conventional MOSFET. Whereas in tunnel FET, there is an additional effect of BT-BT. BT-BT means it is band-to-band tunneling. Okay, there is tunneling of electrons or holes, tunneling from source to channel region. So, in the off-state what happens? Tunneling will not happen. So, very small off-state current known as reverse saturation current is developed. And when you apply a positive gate voltage, you can see here the barrier has been reduced. So, carriers can easily tunnel from the P plus source region to the channel region. Tunneling is made easy with increased gate voltage. Okay. So here a comparison is made between the film FET and one type of tunnel FET. This is indium arsenate and this is gallium nitride based tunnel FET. This material, indium arsenate, gallium nitride means these are mainly for the gate, mainly for the source and drain regions. Okay. So what about the on current here, drain current? For FinFET, it comes in the range of 1000 picoamperes, means comes in the nanoampere range. But for tunnel FET, you can see the on current is very much. What's the difference here? For the on current compared to FinFET, the on current for tunnel FET is low. It is lower. But what about the power dissipation? Power dissipation, you can find an improvement. The tunnel FETs are advantageous compared to power dissipation. Okay? Then other parameters, this is the intrinsic gain value. There also you can find improvement. This is all these readings are taken for a common channel length. Channel length is taken as uniform for these studies. This is also based on the result of simulation done in Centaurus. So mainly the point I wanted to emphasize is that though there is not much improvement in the on current, tunnel FET, T-FET helps to improve the off current, so that the on to off current ratio will be maximized for tunnel FET compared to any other FDP structures. And these are some of the commercially available TCAD tools. Centaurus, developed by Synopsys. Then Atlas simulator is there by Silvaco. Then all kind of physics-based simulation can be done using COMSOL multiphysics. There are various physics modules, even semiconductor modules are available. Now the COMSOL is available through iSTEM portal, free of cost. If you register in iSTEM, a facility provided by the government, then you can freely access this COMSOL tool, so that any kind of device simulation you can perform using this tool. Then there is also Coagenda Genius. Also there are some open access tools. One is provided by Purdue University. Then there is one GSS NanoFlow tool. These tools are open access tools. So what we have seen is that though the technology is progressing as per the Moore's law, now it's kind of saturated. We have already reached 3 to 2 nanometer nodes, right? So beyond Moore's law, what happens? That's the question asked. Still, will the technology scale? Will this continue? So even if it continues, other than this, some of the phenomena that we have seen, like quantum mechanical phenomena, starting from the thermionic phenomena, it may go to some kind of ballistic transport. Okay, quantum effects may become more dominant. That is what can happen even with advanced scaling nodes. Okay, and now the technology is progressing. As I told you, gate-all-around FET, that is already the nodes are marketed. Gate-all-around FET. Another advancement that is going to happen is that complementary FETs. That is, within the same gate-all-around FET, you can alternatively use N-type and P-type devices. That is, we have seen that nano stacks of devices in gate-all-around pattern. So, there you can stack complementary N-type, P-type nano devices. Okay, that is another major invention, that is waiting. Okay, complementary FETs. Then tunnel FET, as I told you, there are still some difficulties. So it is not yet marketed yet. Still in the research phase. So in order to offer better integrity, electrostatic integrity, scaling and energy efficiency, there are advanced architectures are in the pipeline. And also, I had shown you the material level, architecture level, there are improvements happening. You might have heard of spintronics, neuromorphic devices, and even research is happening in the quantum devices, quantum material devices, etc. So, with the emerging need for AI and computing devices, we hope the technologies will scale down beyond more. Okay. So always this optimization of devices, materials, architectures that is on the progress will embrace new technological nodes and advancements. Okay. Thank you. Any doubts, questions?
Can I ask this? It's like you said the feature size is shrinking, and do you think once it comes to this atomic size, all that we learn till now, all theorems, all this everything, we should unlearn and do a
What I believe is this basic phenomena that will change. So as per that, surely there is going to be some design changes.
even Ohm's law, stand.
The subatomic domain, some of the
Possibly our generation will escape. These fellows will survive.
yeah.
And whatever we have been talking about till now, that will be only for low power applications.
Yes, yes.
Not go for higher. So CMOS may stay,
Yeah.
BJT may stay, and we will stay.
BJT is almost like phased out,
Yeah.
not used in the modern designs.
And for one of the devices we said the width is calculated as height plus this.
Twice the height plus that fin width. Yes. That is actually the effective width surrounding the channel.
Yes, but normally we look at how many electrons can travel together. That is the width of the channel. Correct? So that doesn't fit because electrons will go to like the even if your structure is like the so why is height into this? I don't know. And that why not perimeter of this? Because you are leaving out one.
Actually, in that figure,
Uh,
it was surrounding the two height directions and the physical. That is why it was taken as twice the height plus fin width.
Okay. And when you have that all around stuff, we'll have a control on the current better. I agree with that. But at higher frequencies, it is always that the electrons or the current will go through only the core of the material.
Sorry.
Say, both the areas that you talk is something that I never understood in my video. One is SSD and the other is electromagnetic. Both. So it's my fancy idea. I mean, thought like you have a conductor. Okay, and at higher frequencies, will the current go through the middle of it or through the periphery of it?
That is a sort of skin effect. Yeah.
Ah.
Actually, it is said that for higher frequencies, there is another set of design. I mean, the current paths, patterns will be different. So, naturally, what we look here is for medium or low frequency designs, low power designs. For higher frequency, it is predicted that the RF microelectronics that will be very much, what to say, in the next 7 or 10 years, that will be in very high demand. So, their high frequency effect we have to be considered.
And when we consider that buried channel,
Yes.
whatever is there below that buried channel, it is not contributing any conductor to the
No.
surface.
No.
Then why should we carry that luggage?
That is mainly to avoid the latch-up effect.
Ah.
There can be unnecessary leakage power, substrate currents. That can be avoided.
And you think leakage power they will dominate dynamic power at some point?
Yes, sure. That will happen.
That was nice. And something which may not be related to this. You told something like half.
Actually, when we go from one micrometer node, for example, 1 micrometer to the next node, generally next node is, as a rule of thumb, next node is calculated as 1 by root 2. So that's going to be the next node. But in between, in some years, half of that, I mean, instead of taking 1 by root 2, a value higher than that is taken. That is called as half nodes. Especially in sub-nanometer nodes, that was followed. I mean, still being followed.
And why was CMOS not popular for a long time? Because it was invented somewhere near the invention of transistor.
98.
Right.
Yeah.
But it suddenly sprang up only after the 80s cycle.
98.
So there was a dormant period.
Yeah.
What happened?
Earlier, from 1970s to 80s, all were based on BJTs, N-type devices, mostly. Maybe I think due to the of N-type devices, that might be. Thanks.
Thank you, ma'am, for such an informative session. മാമിനോടുള്ള നന്ദി സൂചകമായി മുന്നോട്ട് സമ്മാനിക്കുന്നതിന് വേണ്ടി ഡോക്ടർ വിനയകുമാർ സാറിനെ സ്വാഗതം ചെയ്യുന്നു. Thank you, sir. ഇന്നത്തെ സെഷനുകൾ ഇവിടെ സമാപിക്കുന്നു. It's been an enriching day filled with valuable insights and engaging sessions. On behalf of the organizing team, I extend my heartfelt thanks to all our speakers, participants and coordinators for making today such a great success. We look forward to welcoming you all tomorrow for day 3, which promises to be just as exciting and informative. Until then, thank you and have a great evening. So, നമ്മൾ നാളെ അസംബിൾ ചെയ്യുന്ന ടൈം 9:15 ആണ് രാവിലെ. നോളജ് സെന്ററിലെ മൾട്ടിമീഡിയ ഹാളിലാണ് അസംബിൾ ചെയ്യേണ്ടത്. ആൻഡ് നാളെയാണ് നമുക്ക് ടെസ്റ്റ് വരുന്നത്. 3 to 4 ആണ് ടൈമിംഗ് വരുന്നത്. AICTE അട്ടൽ പോർട്ടലിലാണ് ടെസ്റ്റ് അവൈലബിൾ ആയിരിക്കുക. 60 to 80% മാർക്ക് വേണം സർട്ടിഫിക്കറ്റ് ലഭിക്കാൻ. താങ്ക് യു.
Black color. Copy, reset. Yeah. Oh yeah, continue. Stop streaming.